In section 7.8 we're going to be looking at inverse trigonometric functions along with the derivatives of the inverse trigonometric functions and integrating inverse trigonometric functions when possible. Some of these inverse trig functions, in order to integrate them, we'll have to wait till we have some other techniques, but we're going to be looking at the antiderivatives, and the antiderivatives result in a solution of an inverse trig function. Now, all of this is pretty interesting because actually none of the 6 basic trig functions, and when we talk about the 6 basic trig functions we mean sine, cosine, tangent, secant, cosecant, and cotangent, has an inverse. And this is because they're all periodic, and if they're periodic and they repeat like that, they're not one-to-one, which means they do not pass the horizontal line test. So let's go ahead and start looking at the 3 basic trig functions, sine, cosine, and tangent, and determine how we start these inverses. Now with the sine function, the first thing we want to look at is a basic graph. So I think we'd all recognize this as the nice old sine function. Well, first of all, for the sine function we have a domain and a range, of course. The domain of the sine function is basically the horizontal axis, so it's all real numbers. And there's a lot of different ways that you can write this. The range goes from -1 to 1. These are bracketed because I can actually reach the points -1 and +1. But the problem is it does not pass the horizontal line test. So if we run a horizontal line through here, we'd see that we hit a lot of points. So it does not pass the horizontal line test. So what I need to do is I need to look at a restricted sine function. So I need to restrict the domain. Now there's a lot of different places that we could restrict the domain to and have an inverse exist. But we have an agreed upon spot that we work with. And basically it's from -π/2 to +π/2. And these need to be memorized. Now if you look between -π/2 and +π/2, this definitely passes the horizontal line test. So we restrict the domain between -π/2 and +π/2. Now when we talk about the inverse sine function and the domain and the range swapping, I base it off the restricted domain. Now remember, inverse sine is synonymous with arc sine. You can use either one of these notations, whichever you prefer. And remember, sine inverse of x does not mean 1 over sine of x. Okay? So for the inverse sine function, remember the domain and the range swap. The domain here is going to be the range of my original, so this is going to go -1 to 1, and my range will be based off my restricted domain, not the regular domain, but the restricted domain. And so this would go -π/2 to +π/2. Notice these are bracketed. These are bracketed. I can reach positive and -π/2. So the important thing to remember is when you're working with an inverse trig function is what is the meaning of that statement. So let's go ahead and look at an example of inverse sine of x. This means what angle, okay, and again, anytime you see an inverse trig function, the question you want to ask yourself is what angle in the interval negative to +π/2 has a sine of x? That's the question. And I want you to write all of these out. So anytime you see an inverse trig function, you need to write out the statement, what angle in whatever interval we're working at has a sine, cosine, tangent of x, and we'll write all of these out. So what we're going to do is we're going to develop these for, we already did sine, so we're going to develop this for cosine and tangent, and of course inverse cosine and inverse tangent. And then if you ever need information about secant, cosecant, and cotangent, you can look them up about the restricted domains and the outputs as well. Let's go ahead and look at the sine or the cosine function next. The cosine function, instead of starting at the origin, starts up 1. And this looks like the cosine graph. Now, as before, it does not pass the horizontal line test, and because it does not pass the horizontal line test, an inverse does not exist. If I restricted this from negative to +π/2 like I did the sine function, an inverse would not exist. So we need to look at this one a little bit differently too. Let's go ahead and state just the regular domain and range for the cosine graph. The regular domain is all real numbers. The regular range is -1 to 1, points inclusive. But remember, an inverse does not exist, so I have to look at a restricted domain. Now again, I can't use the same one as I did for sine because an inverse does not exist. It does not pass the horizontal line test between -π/2 and +π/2. So I have to restrict it differently. And the agreed upon restriction is from 0 to pi, first and second quadrants. So the restricted domain is 0 to pi, points inclusive. So let's go ahead and rewrite then, working with the inverse cosine. Inverse cosine can also be written as arc cosine. And when we're talking about the inverse cosine, we have a domain and a range as well. Now remember, the domain and the range swap between an inverse and its function. So the domain for the inverse cosine comes from the range of the regular cosine function. And then from here, the range of the inverse cosine function comes from the restricted domain of the cosine. So again, we have that question. What does inverse cosine of x mean? And again, you need to write this down every time. What angle in the interval 0 to pi, points inclusive, has a cosine of x? That's what the question means. Okay, let's go ahead and look at the same for tangent. Let's see here. Yep, let's look at the same for tangent. For tangent of x, let's look at the graph. We have to remember that tangent is equal to sine over cosine. So I have to be careful when the cosine of x is equal to 0. Cosine of x is equal to 0. If we scroll up here and look at our graph real quick, it looks like -π/2, +π/2, 3π/2, odd multiples of π/2. So I will have vertical asymptotes at these points. And then when we look at what's going on with the tangent function, we know the tangent function is increasing. We know it's negative in the fourth quadrant, positive in the first quadrant. And this repeats, it's periodic over and over again. Now the thing to remember here is this does not pass the horizontal line test either. Does not pass the horizontal line test. But before we state the restriction that we're going to be looking at, let's go ahead and state the standard domain and range for the tangent function. Well, the range is the easier one here. It goes from -∞ to infinity, and remember, you can never bracket infinity. The domain is a little bit more difficult. Instead of saying what x can be, let's go ahead and say what x cannot be. X cannot be odd multiples of π/2. Well, if we were talking about even multiples of π/2, we'd use 2n, but because we're using odd multiples, we can use 2n plus 1 or 2n minus 1 of π/2, and then of course n is any integer value. So let's go ahead and look at the restricted domain here. If we wanted to, we could try and restrict this differently, like from 0 to pi. But 0 to pi doesn't make as much sense here because if you notice, I kind of split this graph in half. So this is the more obvious choice right here. Okay, and I really shouldn't even put brackets on there. I should put parentheses on top of there because I never actually reach π/2 or -π/2. So the restricted domain is -π/2 to +π/2, and these are open parentheses. Okay, they are not brackets. Let's go ahead and look at the inverse tangent function. Another name for inverse tangent is arctan. And let's go ahead and look at the domain and the range for arctan. Now remember, the domain and the range swap between an inverse and its function. So the domain of the arctan comes from the range of the tangent function. So this goes -∞ to infinity. That means this value of x can be anything. It can be any number. And the range comes from the restricted domain. So my output has to be between -π/2 and +π/2. And again, these are not bracketed, and it makes a difference. So let's go ahead and look at inverse tangent of x. And let's write down what that means. That means what angle in the interval -π/2 to π/2 has a tangent of x. And this is a question that you're going to want to write out every time. And it'll get a little bit tedious, but definitely you will get really good at your inverse trig functions. So that will be good. Let's go ahead and look at quite a few examples. And then we'll start combining some of these ideas. And again, if you need to know anything about secants, cosecants, cotangents, or their inverses, you can look up those restrictions. I don't expect you to memorize those, but I do expect to have you memorize the sine, cosine, tangent domain, and the inverse sine, inverse cosine, and inverse tangent restrictions. So make sure you know those. So let's go ahead and look up the inverse sine of 0. Okay, first thing we do is write out the question. What angle in the interval negative to positive pi over 2 has a sine of 0? That's the question. Now, you cannot go outside of the fourth and first quadrant, because if you think about this in terms of the unit circle, what I'm talking about is negative pi over 2 to positive pi over 2. So this is my restriction right here. I can't go outside this quadrant. You can't get a coterminal angle to any of these solutions. You have to get an angle that lies between negative pi over 2 and positive pi over 2 points inclusive. Well, it looks like the obvious answer here would be 0. What angle between negative and positive pi over 2 points inclusive has a sine of 0? And the answer is 0. Let's look at another one. Let's look at the inverse cosine of 0. Okay, this will mean what angle in the interval 0 to pi points inclusive, this is my restriction now, has a cosine of 0. Well, cosine of 0 between 0 and pi will be right up here at our 90 degrees. So my solution that we're looking at is pi over 2, and we do work in radians, so let's keep these values in radians. So get another one. Inverse tangent of -1. This means what angle in the interval negative pi over 2 to pi over 2, and notice these are open parentheses, these are not brackets, has a tangent of -1. Well, if we talk about tangent being negative, tangent is only negative in the fourth and the third quadrant. So I definitely need to be in the fourth quadrant here, but I can't go all the way around the unit circle to get there. My solution here is negative pi over 4. So the way this is going to look is this value, negative pi over 4, has a tangent of -1 because the sine and the cosine are the same except for the positive and negative value. Cosine is positive, sine is negative. Now, one thing I don't want you to do is say, oh, well, that's the same as 7 pi over 4. You can't do that because I went outside this restricted region to figure out what that angle was. So you can't go outside and look for a coterminal angle there. Let's go ahead and look at a few other examples as well. If you recall from our previous lectures about inverse trig functions, or actually not inverse trig functions, but inverse functions in general, if we have a function f of x that has an inverse g of x, then f of g of x is equal to x, and g of f of x equals x. And this is true for inverse functions. Now, it's only true for trig functions inside the restricted domains. So let's go ahead and look at this. Now, this applies to all trig functions. I'm just going to use the example for our inverse trig functions. So let's look at the inverse sine of the sine of x equals x only under restricted conditions. And this is going to be true for the sine of the inverse sine of x as well. This is equal to x only under restricted conditions. This will only be true. So we have to make sure that we keep track of those restricted domains.